Okay, we are going to pick up where we left off in the previous video. We are still talking about graphing rational functions. If you remember in the previous video, we said our first step is to always factor the numerator and the denominator. And then from there, we can kind of go through and find our domain restrictions, our vertical asymptotes, the zeros, which are the x-intercepts, and then the horizontal asymptotes, which is where we are comparing the degree of the numerator to the degree of the denominator by using a little chart that we're given. And there's one new element that I want to introduce to you here today. It was just a little bit too much information in the previous video to throw this idea in. And so I purposely left out this idea that holes can occur in these graphs. Okay? In fact, after you have factored the numerator and the denominator, the very first thing that you want to identify is you want to check for holes in your graph. We call that point discontinuity. Okay, I'm just going to draw a small example of what we're talking about so that you can kind of see. Holes are typically something that you would not be able to identify if you were graphing the function on your calculator. You typically wouldn't be able to see that unless you knew there was a hole in that location and you zoomed in close enough. But it is possible to have a graph and there is a small little pinhole kind of left out of the graph at a certain x value. Okay, that's what I'm talking about when I'm talking about a hole. Okay, and so here's how you go about identifying a hole. Okay, you're going to start the same way we start all of these problems. You're going to factor the numerator and the denominator. And here's what a hole is, though. A hole is, if you notice, once it's factored, if the numerator and the denominator share a common factor, then you're going to set that factor equal to 0, and the hole would occur at that x value. Okay, so for example, I have a problem here off to the side that is worked out here. Okay, you can see that right here was the original problem. You can see in this step I factored the numerator, that's a difference of 2 squares. And then I'm looking to see, is there a common identical factor in the numerator and in the denominator? Okay, I would encourage you to circle any common factors that you see. Okay, for example, there's an x plus 2 in the numerator and an x plus 2 in the denominator. That is telling us that this graph is going to contain a hole in it. Okay? So then you would set that factor equal to 0, and that would reveal that that particular graph contains a hole where x equals -2. Okay, now here's something worth noting though. And this is the reason that you always want to check for the holes right off the bat. Okay, if a function has a hole, there will not be a vertical asymptote or an x-intercept at that x value. Okay, so the holes kind of trump the vertical asymptotes and they trump the x-intercepts. That's why you circling them will help you remember that you have used that up already. So in this example that we just looked at, typically we say then that the vertical asymptotes are any factors in the denominator that have variables with them, which you can see there is a factor in this denominator. However, I used that factor up as a whole, so I would not say that there's a hole where x equals -2 and that there's also a vertical asymptote where x equals -2. Okay? So if you've used it as a whole, then we do not identify it as a vertical asymptote. Same thing, we would not identify -2 as being an x-intercept. Okay? All right, so that's kind of the only new piece to this particular lesson. I just want to look at this example here where it's talking about vertical asymptotes. Just to run through, factoring the numerator, you can see I pulled a GCF out and then factored that difference of 2 squares into this here. And looking at the denominator, I pulled a GCF out in x, and then we factored that trinomial down. Okay, I'm looking for holes. If I were going to identify holes, there would definitely be a hole right there where x equals -3. Okay, but you'll notice that I used up one of the factors that was in the denominator. However, there were still 2 factors left in the denominator that had variables in them, and that's where I was getting these 2 vertical asymptotes that you see here. Okay, keep in mind, if there is just an x by itself, that is what is producing the vertical asymptote of x equals 0, and this one is x equals 5. Okay? All right, and then the other thing I want to mention here, and we'll just look at a few problems from start to finish. There could be a scenario where you are given the problem and maybe it's already factored, okay, or partially factored. Okay, now that's great from the standpoint of holes and vertical asymptotes and your x-intercepts, but where you have to be careful is when you're asked to identify the horizontal asymptotes. These are the ones that you actually want the problem to be in standard form, not in factored form. So if the problem started out like this here, you would want to be very careful and not mistakenly say that the degree of your numerator is 2 and the degree of your denominator is 2. Instead, you would need to ask yourself, well, if this were multiplied together, actually the degree of the numerator would be 3, and the degree of the denominator would be 3. If you recall that chart, it said if the 2 degrees are equal to each other, that's when we are making a fraction out of the lead coefficients. And the lead coefficients were even a little bit hard to detect from the original problem, but if you multiply it together, you can see the lead coefficient of the numerator is a 4, and the lead coefficient of the denominator is a -3. Okay, so let's just try a few of these here from start to finish and see if we're okay with just adding in this new element here of finding the holes, if you will. Okay. All right, so our first step, I kind of summarized the steps, and I think the order that I have these steps in is a really nice order to kind of go through this. It's not necessarily the order that the blanks are in off to the side, but I think this is the most efficient way to kind of run through these problems here. So we're going to start by factoring the numerator, factoring the denominator, and then we want to, right off the bat, identify any holes that we might think exist on this graph. Okay, and you want to identify those by circling that common factor in your numerator and denominator. Okay, and then we'll set that factor equal to 0, x equals -2. Okay, the next thing that we should do then, after we've identified holes, is we should go ahead and say what our vertical asymptotes are. Remember, both vertical asymptotes and the domain come from any factors in the denominator that have variables in them. So I want to make sure, though, that I'm not counting the factor that I used up as a whole. So I'm only looking at the x minus 2 factor. I would say that the vertical asymptote is at x equals 2. And then I also would say that my domain is all real numbers, but x is not allowed to equal 2. As you find these asymptotes, you definitely want to place those onto your graph. So we would want to put a dotted vertical line. We want to label that at x equals 2. Okay, step 4 here, we're going to find the x-intercepts, which are the zeros. You recall those come from the numerator. Okay, so now we're going to be looking at our numerator. You want to look at it in its factored form. And you want to pick out any factors in the numerator that have a variable in them that have not been used up as a whole. Well, the x plus 2 has been used up as a whole. The only other factor that's in the numerator is a 3, but that doesn't have any variables with it. And so in this example, we would simply say that there are none. There are no x-intercepts to this graph, so it's not going to cross the x-axis at all. Okay, finally, when we state the horizontal asymptotes, this is where we're using that little chart. Okay, we would want to revert all the way back to the problem where we are in standard form. We're going to want to identify the degree of the numerator, that's a 1. The degree of the denominator, that's a 2. This is falling into the category where the numerator degree is less than the denominator degree. And so that would have us say that we have a horizontal asymptote, and it's going to be located at y equals 0. Once all of our blanks are filled in, and we've placed all the asymptotes onto the graph, and if there were any x-intercepts, those also onto the graph, the last thing that remains is for us to use our calculator to help sort of draw in these curves here. Okay? So we want to go back. I think it's easiest to type the equation in before any factoring has occurred, although you do want to make sure that you are grouping the entire numerator in parentheses and the entire denominator in parentheses. Okay? And then we're just simply going to look at this graph to help us kind of sketch these curves around the asymptotes here. Now, there is one piece here to this. We did say that there is a hole on this graph. Okay? Remember we said there was a hole at x equals -2. Okay, so we need to make sure at the end, it's really, really easy to forget this, that we go back onto the graph that we just drew, and we erase a little spot, and we put an open hole in right where x equals -2. Make sure you're putting this hole in on the graph. Okay, so you want to go to where x is -2, but then you want to slide down to where that would fall on the graph. Okay. And then just kind of put an open circle right there underneath where x equals -2. Okay. Most of the process here is the same as what we did in the previous video, with the exception of holes here. Okay, so let's just try a few more here. We're going to start by factoring. I'm going to pull out the GCF from the numerator. I'm going to reorder the denominator so that we've got it in descending order. And then I see that x squared plus 16 will factor as a difference of 2 squares. And also, I've got a trinomial in the denominator, lead coefficient of 1. So I want to factor that into x minus 4 and x minus 1. Okay, I should be pretty good here to identify any holes if they in fact exist. And it certainly looks like I'm seeing a common factor, x minus 4 in the top and x minus 4 in the bottom. So if that were set equal to 0, that would reveal there is a hole on this graph where x equals 4. Okay. Now we're going to do our domain restrictions and the vertical asymptotes. Recall those come from the denominator. So when I look at the denominator, I want to ignore the factor that was involving the hole, and I only want to look at the x minus 1. If that were set equal to 0, there would be a vertical asymptote where x equals 1. So I'm going to go ahead and place that and label it on the graph. Also, the domain, all real numbers, x is not allowed to equal 1. Okay, the zeros. I'm now looking back at the numerator. I want to ignore any factors that I've used up as holes and any factors that do not have x's in them. But there is one factor in the top that we should look at for our zeros, and that's the x plus 4. So if that were set equal to 0, that's telling us that this graph is indeed going to cross the x-axis at x equals -4. Okay, all that we're left with now are the horizontal asymptotes. This is where we want to go all the way back to the problem before any factoring occurred. And you want to be careful because if you look at this closely, you'll notice the denominator was not in descending order. Okay, so when we're doing this, we're going to say the numerator degree is 2, the denominator degree is 2. This is the scenario where the degrees are equal to each other. So again, be very careful. We want what would be the lead coefficient. That's a 2, and technically in the denominator, it's a 1 if that were reordered. So this means we have a horizontal asymptote where y equals +1. So again, placing that on the graph and labeling that. And then we're down to our calculator here. Okay, whoops. So on the calculator, we will type this in, 2x squared minus 32 divided by, doesn't have to be in descending order when you are typing this in. That was a plus x squared. There we go. Okay. Hit graph. We're just going to examine that to help us kind of fill in the graph. Remember, we do have an x-intercept here. We want to make sure when we're drawing this that we're above the x-axis and then we're passing through that zero. We also want to come over here. It's hugging these asymptotes but not touching or crossing them. And then we did also have a hole on this. So in the end, you want to go back and say, where did we say the hole was? It's at x equals 4. So you want to come to where like 4 is on the x-axis, but then you want to go directly above. That's the part that you're going to want to erase. Erase that section of your graph and just insert an open hole there. Okay. All right, let's go ahead and jump to the next page. We'll skip that one there, and let's just jump to this next page here and take a look at a couple of these graphs. Look a little funny here. Okay, in fact, I think if we just do example 5, we might be just fine here. Okay, this is really throwing everything at you with factoring. We've talked a lot about factoring, so you need to be comfortable with recognizing what you need to do given how the problem looks. When we go to factor this, you'll notice this numerator is starting out with 4 terms in it. We've discussed anytime you have 4 terms, that's when you're going to start factoring the problem by using the process factoring by grouping. Okay, so I'm going to be grouping together the first 2 terms. I'm going to group the last 2 terms, and then I'm going to pull a GCF out of the first group, and then I want to pull a GCF out of the second group so that what I'm leaving behind will be identical quantities. Okay? My denominator for this is just a difference of 2 squares, so I can factor that. Now I'm going to pull the x plus 2 out of the numerator. That leaves behind x squared minus 9. And sometimes you think you've gone through so many steps that you've got to be done factoring. Make sure you always examine each of your factors and make sure that there's nothing more that you can do. If you look closely at this x squared minus 9, that can be factored down further into an x plus 3 and an x minus 3. Okay, so we have a lot of factors here to kind of look at. Okay, once it's completely factored, our first thing to check for are holes, and this particular problem has 2 holes to it, okay, because it's got 2 sets of common factors in the numerator and denominator. Okay, so we've got a hole at -3, another hole at +3, but look at what we circled. We've used up every single factor that's in the denominator that had a variable with it. So that tells me that I'm not going to have any vertical asymptotes for this problem at all. And as far as my domain restrictions go, I'm not going to have any domain restriction. Well, that's not true. That's not true. My domain restriction has to be where there are holes. I apologize. Okay. Your domain restriction is always a combination of your holes and your vertical asymptotes. I'm going to flip back to this previous example we did and see if I did that. I don't know that I did. Oh, you know what? I should have put the hole there as a restriction. I mean, if you think about what a hole is, it's a place on the graph that we're saying the graph is not allowed to exist. That's why there's a hole there to begin with. So when we're doing our domain restrictions, we always need to make sure that the restrictions are not just the vertical asymptotes, but they're a combination of the vertical asymptotes and the holes put together. Okay, and I didn't think that I had mentioned that, so I apologize about that. Okay, so on this problem, we said there were no vertical asymptotes. However, here we said there were 2 holes. That's why I need to list those down here as my restrictions. Okay, let's go back and look at our zeros here real quickly. Okay, the zeros are our x-intercepts. That's anything left over in the numerator once you've already accounted for wholes. There's still an x plus 2 factor in the numerator, so that means that this graph is going to cross the x-axis where x is negative 2. Okay, and finally, horizontal asymptotes. I'm going to go all the way back up to the beginning. Looks like the numerator degree is 3 and the denominator degree is 2. Okay, so anytime our numerator degree is greater than the denominator degree, that's when we have no horizontal asymptotes. So in terms of graphing this, it doesn't look like we have a lot going on here right now until we get to the calculator. We have one little x-intercept plotted. There are no asymptotes at all. This graph is probably not going to look how you would expect it to look when we graph it here. Looking at the equation, you might expect it to look pretty complicated. But if we were to type this in, x cubed plus 2x squared minus 9x minus 18, and we're dividing that by x squared minus 9, actually a pretty simple looking graph. Okay, it just looks like a linear graph, and really, if you go back and look at what we crossed out here, because there's a hole at negative 3 and positive 3, this is really just the graph of the line y equals x plus 2, except it has 2 holes in it. Okay, so it's going to go through that x-intercept that we had there, but we do have to make sure that we go back and we erase a spot right above 3, and we erase a spot right below negative 3, so that we're putting those holes onto the graph. Okay? So once again, one thing that I had left out at the beginning is when you are doing your domain restrictions need to now be a combination of any of your vertical asymptotes and any of your holes. Okay? Those two things combined together. Okay, your assignment is worksheet 8.4B.